Do not go gentle into that good night. Old age should burn and rave at the close of day. Rage, rage against the dying of the light. In those immortal words of Dylan Thomas, I thought were a good way to start this session, that is asking the question, do we really want to live forever? In other words, we are talking about both the plausibility and the desirability of the quest for, if not immortality, at least extending our natural lifespans. And in order to address this question, I've got four people who are far more qualified than myself, a mere futurist and economist. All four of them are doctors, and we're starting right on the end over there with Dr. Jose Cordeiro, who's the Vice Chair of Humanity Plus. We've then got Dr. Hanan Al-Suwaidi, the Chief Business Officer of the Dubai Academic Health Corporation. Sitting next to her is Dr. James Kirkland, the Noaber Foundation Professor of Aging Research. And next to me over here is Dr. Alex Zhavoronko, the founder and CEO of Insilico Medicine. So to kick us off today, Dr. Jose has prepared a few words as to what he is doing with Humanity Plus right now. So let's hand over to him.
Okay, good morning to everybody. I just want to share a few things happening in the next few years. I work with different organizations, including Humanity Plus, that I am the Vice President internationally. I am an engineer from MIT, but I moved from the energy field into biotech and longevity. But also with the Millennium Project, I coordinate the group of Latin America, Spain, and Portugal, looking at trends. And we just published a study about the year 2050, where we have three scenarios. In one of those scenarios, humans will already be immortal. I am one of the founding faculty of Singularity University with Ray Kurzweil, and we talk about immortality openly with our students at NASA, Ames in Silicon Valley with the support of Google and other companies. Why are we doing this? Because we have incredible results in the last few years about life extension. We have been able to almost double the life expectancy of mice, almost multiply by 4 the life expectancy of mosquitoes, and by 10 the life expectancy of worms in the last few years, and this will continue. In fact, the Nobel Prize in Medicine, the year 2012, Dr. Shinya Yamanaka, he discovered some genes that control aging, and you can accelerate aging or you can reverse aging. I actually was with him 2 weeks ago in Madrid, where we gave him an award from the Medical Academy of Spain. Also, we have other scientists following these technologies, like David Sinclair at Harvard, and he has been able, with his students, to rejuvenate organs. Not just to rejuvenate cells, but to rejuvenate organs. They are doing experiments with mice and soon with humans. Because today we believe, many people, that aging is a disease, but it is curable, and we should be able to cure aging in the next few years. In fact, aging is the major cause of all other diseases. If we stop aging, we will stop cancer, heart attacks, dementia, Alzheimer's, etc. The #1 risk factor for most diseases is aging itself. In fact, we know that there are immortal cells. Cancer cells, it was discovered in 1951, that they stop aging. Cancer cells are considered biologically immortal. And cancer cells did not go to university. Cancer cells didn't go to MIT, and they discovered how not to age. So it is not that complicated, because cancer cell doesn't even know how to read. And they didn't spend $1, but they discovered immortality. But not only cancer cells are immortal, but also the best cells in the body, which are the germ cells for reproduction. And you all have germ cells, and those cells are biologically immortal. They do not age. Additionally, we have small organisms that are also considered biologically immortal, like hydras and some medusas and jellyfish. And the most beautiful thing is that the first life forms in the planet, bacteria, that reproduce symmetrically, they do not age also. They are considered biologically immortal. So life appeared to live, not to die. 4 years ago, with an incredible mathematician from Cambridge University, and I also went to Cambridge, but Cambridge, Massachusetts, we decided to write a book about this. And our book, in Spanish first, called The Death of Death, came out in Spanish, in Portuguese, in French, a bestseller in all these languages. In fact, when it came out in Spanish, was simultaneously #1 and #5 bestseller in paper and in Kindle. Now it's in many other languages. It just came out in Russian. If you can read Russian, in Russian it is called Death Must Die. very Russian style. Death must die. And now it just came out in German, and it is the #2 best-selling book in Germany, according to the Amazon ranking. So I'm very excited, and also in Chinese and in many other languages. Many of these ideas are developed on what my friend Ray Kurzweil talks about, the singularity. And I have here his next book that will come out next year. The singularity is nearer. In this book, he talks about immortality in the year 2045, which is also the year of the singularity. This is based on exponential advances in technology. And Time Magazine and many other publications have become covering this idea that by 2045 is the year when man becomes immortal. But for the ladies here, you will be immortal too. Everybody who wants to be immortal will be able to. There are 2 dates in these ideas of Ray Kurzweil, who is also an engineer from MIT, my alma mater. He talks about the year 2029 to 2030, when we will reach longevity escape velocity, or the Methuselarity, the singularity of Methuselah. If you make it to 2030, you will basically live long enough to live forever, if you want to. Because even though we will still be aging, we will get 1 extra year per year we survive until 2045, when we will have rejuvenation technologies. And we will have not 1 but 2 immortalities: immortality of the hardware and immortality of the software. We will also be able to upload our brains into other substrates. This is happening because of exponentiality. Everything is faster, smaller, cheaper, and better. And many of you who have my age probably know this. This is the IBM punch cards that I used 40 years ago. This was 1K of memory, 1K of memory. And then I also used this. Was also 1K, but this 1K was better because you could erase. In Spanish, we say K. 1K is 1K. So 40 years ago, I had 1K mechanical, 1K electromagnetic, 1K, and 1K makes 1 kaka. 1 kaka we had of memory. And look at how it has been advanced. It has gone from kaka to 512 kakas to 1.4 mega. And here I have a pen drive of 1 terabyte. 1 terabyte. This has happened in 40 years. We went from kaka to terabytes. You will remember me in the next 20 years, and you will remember kaka. But this will be the kaka of the future. This 1 terabyte will be kaka in 20 years. This is happening now in biology. Biology is changing also exponentially thanks to the sequence of the human genome. The first human genome cost over $1 billion to the US government alone, altogether $3 billion, and it took 13 years. I just sequenced my genome with a company which is also based here in Dubai, Dante Labs. This is an Italian company, but they have a research lab here in Dubai. And I just sequenced my genome. You can do it very nicely, cheaply here in Dubai. And these are my results that we don't have time to talk about. But now that we can sequence the genome, we will be able to discover the diseases you will have. Like Microsoft says, we will solve cancer because this is a technical problem. Or also Google. Google says that we will solve death because death is a technical problem. And that is how we will solve death. Or Facebook, Mark Zuckerberg, we will cure all diseases in the next 2 decades, including aging. Or Tim Cook said that Apple will be remembered in the future for what they will do in health and medicine. All the companies are moving into health issues. Jeff Bezos, Amazon, invested $3 billion with other people. All the companies in technology are moving into health because this market is already over $8 trillion, and this will be the biggest ecosystem in the planet. The biggest industry ever in human history is the longevity industry. I don't know what you do, and I don't care. If you are not into longevity, you are not into the future. This will be the largest industry in the planet in the next 20 years. Even Saudi Arabia, the neighbor here, has created a foundation called Evolution Foundation, Health plus Evolution, to cure aging in Saudi Arabia, $1 billion. And in Abu Dhabi, for what I understand, they are also creating a fund, $400 million for health issues. Anyway, I plan to be younger in the future, not through a Russian application, not because of FaceApp from Russia. I plan to be younger because we will have rejuvenation technologies. And I finish with this beautiful Chinese word. If you understand Chinese, this Chinese word means crisis. We are in the middle of a crisis, the biggest crisis in humanity. And there are 2 characters to crisis. The first character means danger, danger. But the second character means opportunity. We are living in the most incredible time in human history. We will do the dream of humanity from the beginning, immortality. We are between the last mortal generation and the first immortal generation. Where do you want to be? Thank you very much.
Well, now that we've thrown down the gauntlet, we now want to turn to what Insilico medicine is actually doing at the moment with regards to fulfilling some of those challenges that Jose has spoken about.
Hi, everybody. First, I have great pleasure to be here, and thank you very much for inviting me. I, of course, know Jose for many years, and I switched into aging research from IT about 20 years ago. And now I'll try to bring you back to reality. So of course, we're not going to cure aging within the next few years. It's impossible. And once you understand how drugs are discovered and developed, you will understand why. So when you start really getting into the field and doing what we do, you realize that those rosy glasses break every time you do an experiment. And there's more failures than successes out there. So I'll try to, well, since I run a company in Insilico Medicine, I need to make those disclaimers, no forward-looking statements, not investment advice. As a matter of fact, you, at this point in time, won't be able to invest in the company. And also very important to mention that, of course, I am very dedicated to longevity, so everything that I do is going into longevity, and you can read my longevity pledge on longevitypledge.org. I'm announcing it next week. So basically everything I earn will go into longevity, but mostly businesses. So what is important is in around 2014, the technology called deep generative reinforcement learning emerged and enabled us to outperform humans in image recognition, voice recognition, text recognition, and even generation of beautiful art, deep fakes. And now you can use this technology pretty much everywhere. So I founded a company called Deep Longevity. It's a spin-off out of Insilico. It uses deep learning to build aging clocks, predictors of age, biological age, and even psychological age, using multiple different data types. And we published multiple papers on that, hold multiple patents. It then was acquired by a publicly traded company in Hong Kong called Endurance. And at Insilico, we use this technology to identify biological targets, formulate hypotheses of disease hypothesis, generate molecular pathways, and also generate small molecules with the desired properties, so generate novel chemistry. So how can we use this technology to rapidly discover and develop dual-purpose therapeutics that can be implicated in aging and disease at the same time? In the most credible way. So for that, we built Insilico Medicine. So Insilico Medicine, we originally were founded in Baltimore at the Emerging Technology Centers at the campus of the Johns Hopkins University, so my alma mater. Then we scaled globally. We have a very substantial presence in Asia. And currently, we're actually building a site here in the UAE. So that's why the THOB, and we're trying to be very culturally friendly. By the way, if you are wearing those pins, probably should wear them on your right side, not on the left side, because here everything is right. And we built a company which is approximately 260 people globally. We're growing. We're growing here. Hopefully in November we'll be able to announce the R&D office here. And we also rely on the ecosystem of contract research organizations, predominantly in Asia, that nowadays allow you to do experiments in a very distributed way, in a very similar approach as Apple, designed in California, made in China, but now you can design in California or design anywhere and distribute the workload globally, so you don't need to build the laboratory infrastructure. And that gives the opportunity and the possibility for countries like the UAE to actually kickstart their drug discovery programs. So you don't need to have an established pharmaceutical infrastructure to discover drugs. And what we've developed is a company which is AI first. So we have multiple AI teams globally that allow us to do generative AI, so deep fakes on chemistry, deep fakes on biology. We do also generative chemistry, so designing small molecules with the desired properties. And I partnered with Dr. Ren, so Harvard PhD, 11 years at GSK, and then he listed a company called Medicilin, took it to $8 billion cap, and then joined me on this quest. So he built a drug discovery team, which allows us to discover drugs. And this is the most important slide in this presentation. So again, once you get into drug discovery, you realize how long and risky this process is. So if you are, if you have any ambition to build a biotech or a biotech ecosystem here, you need to know this slide. The journey takes you about 12 years from discovery of the target to launch. Fails 99% of the time if you start from target discovery, and fails 90% of the time once you're in human clinical trials. So what Dr. Kirkland is going to present, he's also running clinical trials. That's why he has to be, completely out of the companies, very, very honest and unbiased approach. But he is running clinical trials for drugs that have been discovered, many, many years ago, 30-year-old drugs. If you are discovering a drug from scratch, you are much more likely to fail, and the cost of this process is going to cost you approximately $2 billion at the very minimum. So that's how much it costs big pharma. So what we did when we started Insilico, we looked at the many steps that could be accelerated or improved using AI and next-gen AI. So we looked at how drugs are discovered in a traditional way and tried to go end-to-end and automate. So there are many steps that can be automated using AI. Actually, many of you have heard about AlphaFold. So you see heat identification, there is a step called obtain crystal structure. So what DeepMind did as a true breakthrough, it's a revolution, but it's still a small, tiny piece of the puzzle. And so far you don't see, so AlphaFold is 4 years old, you don't see AI-generated drugs based on AlphaFold proteins in human clinical trials yet, or even in late discovery stages. So what we tried to do, we looked at all of the steps. We separated them into two areas, so biology and chemistry. So AI discovered drugs, they have novel targets discovered by AI. AI-designed therapeutics have novel chemistry designed by AI for the targets that we identified. Again, the major problem is actually target discovery. And we decided to build a pipeline using AI, which is seamlessly integrated. So internally, we use it as an integrated platform. Of course, big pharmaceutical companies have those steps separated. So we usually have software products. Currently, 9 out of the top 30 pharmaceutical companies are using us and our software for different purposes. So you can use multiple different data types to identify targets, formulate the hypothesis of disease, then generate small molecules, and then predict the outcomes of clinical trials. So internally for us, it's one exercise, but we also have 3 products that pharmaceutical companies use. And now I'm going to talk about my kind of most interesting project that is real and that is currently in human clinical trials. But we started this project very, very early, so from hypothesis generation, so about 3 years in the making. And in 2020, we decided to go after the grand challenge that is, again, very, very rare. So in big pharmaceutical companies, this happens very, very rarely. And in biotech, usually that's also disconnected. So one biotech company discovers the targets, or academics discover the targets, and then big pharmaceutical companies design the molecules. We decided to combine those steps and also go after a very broad therapeutic indication and aging itself at the same time. So we chose fibrosis, not only lung fibrosis. We purposed the drug to lung fibrosis, but fibrosis is the process that happens in every one of your bodies during the course of life. Actually, every time you scratch your skin, there will be fibrosis. You will see a scar forming, and fibrotic tissue will form to substitute for the lost tissue. So that's what's happening during aging as well, and that's happening in a dysregulated way in lung fibrosis. So IPF is an age-associated disease. The average age of onset is 55, 65. Very important disease, very rare, but it kills within a few years. So people with IPF suffer dramatically, It's also a huge market, about $3 billion, even though it's a rare disease. There are 2 approved drugs. None of them solve the problem. So again, solving aging, we need to be very careful when making those claims. And what we did, so this is kind of more of a scientific diagram, how we did this. So we trained a predictor of biological age on multiple tissue types using gene expression data, so transcriptomics, for those of you who are in science, and then retrained those predictors on many samples of people with different fibrotic diseases. So we looked at protein targets that are implicated in fibrosis and in aging at the same time. Then we used our PandaOmics platform, it's a target discovery platform, to assess the novelty of those targets, found the targets that are moderately novel and have high confidence, prioritized 20 targets, tested 5, all 5 of them worked. We prioritized 1. And we took this one target with our own chemistry all the way into preclinical candidate stage in under 18 months. So that's, in my book, it's a record to my knowledge, because also the target is novel, so you need to also do your own chemistry. We also, for the IPF indication only, we spent about $2.7 million, which is much less than the big pharmaceutical companies spend up until this time. And to my knowledge, that's the first time AI was used to identify the target, generate small molecules, predict synthetic route planning. We completed many experiments, so at least 8 in vivo efficacy experiments to develop preclinical candidates for lung fibrosis, kidney fibrosis, and skin fibrosis. And right now, we also are in phase 1 human clinical trials. We did a small phase 0 clinical study, so 8 healthy volunteers in Australia last year, because the target is novel. We want to ensure that we understand it very well. And we've delivered 8 preclinical candidates since February 2021. Again, to my knowledge, it's a record, and this year we expect to deliver more. We also raised $415 million from some of the very sophisticated healthcare investors and also biotech and AI investors, more than 70 of them. So, of course, we've been quite validated. Over 120 research papers published by my group. And if you are interested in learning about what we do in longevity and how doctors today can get into longevity while there is nothing that works, with the exception of maybe rapamycin, metformin, and a few other things that were tested in ITP program by NIH, and what Dr. Kirkland is going to show you is in clinical trials, also very promising. But there is nothing you can really do today. But you need to be prepared. So we have 2 CME accredited courses that you can take for free on longevity degree. And here are my contact info. Again, we are very focused on the Middle East. I now call it Middle Earth because it's very neutral and it's a great place to be. To start a business, to bring your R&D staff here. And right now it's a gold rush to hire R&D staff in Eastern Europe, especially in AI because of the war there. And yeah, we're building an Abu Dhabi office, and also I just got my golden visa here in Dubai. So would really love to contribute to the economy here. Thank you so much.
Thank you. We're now going to turn to Dr. Kirkland to tell us about his work and as he described it to me backstage, trying to improve health spans for people.
Hi, thank you very much. It's nice to be in Dubai again. I'm a very simple physician, a geriatrician. I got tired, though, of prescribing better wheelchairs, walkers, and incontinence devices. So I went back to school and did a PhD in biochemistry and cell biology. And I've always been interested, ever since I was a little kid, for reasons I don't understand, in what aging is and how it progresses, and whether there's something we can do to delay, prevent, or alleviate multiple conditions by targeting aging processes. So aging begins before conception. Down syndrome, for example, is a disease that's related to fundamental aging processes, and it's due to aging of the egg in the mother before it's even fertilized, and it turns out to be a senescence-associated disorder, Indeed, we're hoping to begin clinical trials soon in Down syndrome with agents that target fundamental aging processes. Fundamental aging processes are activated by resuscitating babies with high oxygen at birth, and this seems to predispose to asthma when kids are 2 to 4 years old, that is linked to accelerated operation of fundamental aging processes in the lungs. So fundamental aging processes can occur and be accelerated at sites of etiology of multiple diseases at any point in the lifespan. And these processes tend to be conserved across all of the vertebrates, and many of them occur in invertebrates. So aging, as we've heard before, appears to predispose to the bulk of conditions. These fundamental aging processes appear to underlie or contribute to the bulk of conditions that cause most morbidity, mortality, and health costs in both the developed and the developing world. They also affect agriculture, defense, and everything else. So it's now feasible to target some of the fundamental processes that are linked to aging. We call them pillars of aging or fundamental aging processes. There are anywhere from 4 to 13 of them. They're all tightly interlinked, such that if you target one, you tend to affect all the rest, sometimes in the same direction, but not always. And there are at least 35 sets of interventions now through which these processes can be targeted in preclinical models. So it's beginning to look like in preclinical models, that is human tissue explants or various animal models, that by targeting some of these processes, it may be possible to delay, prevent, alleviate, or treat multiple conditions across the lifespan. So the particular interest that we've had is in ablating cells that are called senescent cells. Senescence is a cell fate, like cell division or cell differentiation into specialized cell types. It occurs across, again, all the vertebrates. It occurs in some invertebrates. So it's a damage response, and it's a defense against cancer. And senescent cells form, for example, in the placenta, and they produce the factors that drive the baby through the birth canal. They're important in tissue remodeling. So you don't want to stop senescence from forming. In fact, if you mess around too much with senescence in the wrong way, you will cause cancer. The same way as if you target certain other fundamental aging processes at the wrong phase in the lifespan, you will cause cancer. So one of the things that we wondered why do some senescent cells, all senescent cells, appear to produce a range of proteins and peptides and non-coding nucleotides and other factors. Around 30 to 70% of them produce damaging factors, yet they themselves don't die. This is very much like some kinds of cancer cells. So we used early bioinformatics approaches back in the, around 2013 to look at proteomic data we had. And we asked the question, why do the 30 to 70% of senescent cells that are killing cells around them survive despite the fact they're killing the cells around them? We found there were pro-survival pathways that senescent cells use to defend themselves against committing suicide. And we found, again, using early bioinformatics approaches through the Broad Institute, that we could, that there are a range of pre-approved drugs and natural products where there are known safety profiles, short elimination half-lives that can be given orally, that transiently disable these pathways. 2 hours is all you need. And that allows the damaging senescent cells that persist and aren't removed properly the way they should be by the immune system to kill themselves, to commit suicide. So these kinds of interventions can be given intermittently. It takes a week to 6 weeks for new senescent cells to form. So typically in preclinical animal models and now in the clinical trials, we give these agents once a month or once every 2 weeks. We originally found 39 of these agents using these early bioinformatics approaches. They all turned out to be senolytic. We decided to focus on particular ones to take through to clinical trials because of their safety profiles and because of their low cost. So one of the, and we found, as is the case with other agents that target fundamental aging processes like sirtuin agonists or NAD precursors or CD38 inhibitors, or what we call xenomorphics. Rapamycin and metformin are drugs that are xenomorphics. They inhibit the secretory, or at least part of the secretory state of tissue-damaging senescent cells, where senolytics actually kill the cells. That there are at least 70 conditions in preclinical models that we can delay, prevent, alleviate, or treat. And these range across all kinds of conditions throughout the lifespan. So one of the things that's been established is through the National Institutes of Health, they were crazy enough to make me head of it for now, is a translational geroscience network. So there are well over a dozen institutions across the US involved in this, including Mayo, Harvard, Hopkins, University of Texas, Michigan, Minnesota, and a long list of others, where we're trying to do clinical trials in parallel rather than in series of agents that target fundamental aging processes. Currently, we have 30 clinical trials underway. 16 are with senolytics, but we're comparing senolytics to other agents that target fundamental aging processes and trying to look across these conditions which are best. We're no longer using the old-fashioned one drug, one target, one disease approach. The branch of the FDA that's working with us is the group that develops antibiotics. So we're trying, in the case of senolytics, we're trying to kill a cell type, senescent cells. We don't care what the molecular targets are. We care that the cells are killed. And again, like developing antibiotics, we're not going after one disease. With an antibiotic, you can go after urinary tract infections, meningitis, endocarditis, et cetera, et cetera. We're doing the same thing, and the FDA views this in the same way as developing antibiotics. So the trials are for a range of conditions, right from frailty and childhood cancer survivors through to bone marrow transplant survivors who have a lot of senescent cells because they've had high doses of chemo and radiation, adult cancer survivors. There are 3 trials underway for coronavirus because coronaviruses preferentially infect senescent cells. Coronaviruses and other viruses cause cells to become senescent, and senescent cells produce factors that cause neighboring cells to become susceptible to coronavirus. And furthermore, it's in senescent cells that viruses mutate. So the new isoforms of these viruses tend to be generated within senescent cells. This may be the reason why it's the elderly and people with senescence-associated disorders like diabetes or chronic obstructive pulmonary disease who've had cancer treatment who are susceptible for coronavirus. So there are 3 trials underway for coronavirus. There are trials about to begin for chronic HIV syndrome, another viral-related syndrome. There are trials underway for frailty in elderly individuals with a gait speed of less than 0.6 meters per second, which translates to a 2-year average life expectancy, very serious condition. There are trials beginning for glioblastoma multiforme, triple-negative breast cancer, multiple myeloma, and melanoma. There are trials nearly completed for osteoporosis, age-related osteoporosis. There are trials underway that are actually funded by the US Navy for osteoarthritis. It turns out the biggest reason for not being able to man ships or marine units is exercise, resistance exercise-induced bone injury, and senescent cells appear to be responsible. So we hear resistance exercise is good for aging-related things. It probably is, but in excess, any of these things can be damaging. We're working with Axiom and SpaceX and hoping to work with the Emirates Space Agency, looking at generation of senescent cells in astronauts. This is caused by zero gravity and space radiation, especially cosmic and solar radiation, which are very efficient in inducing senescence. There's no way we're going to Mars unless we're able to solve this problem. So we've been working with Brookhaven and the Colorado Space Center and the University of Texas and NASA, looking at this generation of senescent cells in astronauts, especially beyond the Von Allen belts. Astronauts are dying early of age-related diseases. They get an accelerated aging-like syndrome, especially if they've been to the moon, for example. There are trials underway to try to rehabilitate organs from older donors so they can be transplanted into younger individuals, and many other kinds of trials. Across these trials, we're measuring the same body fluid parameters across all the universities and institutions involved. So we're measuring about 150 things in blood, urine, saliva, buccal swabs, nail and hair clippings, microbiome, et cetera, across all the trials, irrespective of the indication for the agent or which agent is being used. We're using a common data analysis facility to analyze results of all the trials, and we're setting up a biobank that we now have 45,000 specimens and that the NIH is going to take over so that we can provide these samples to basic science laboratories for reverse translation. We've established collaborations with groups in Denmark, Sweden, Britain, hoping to establish a collaboration with a group in France, working with Haevolution. Mayo has, of course, a branch in Abu Dhabi where work is beginning on senescence and senolytics and bone marrow transplantation, cancer treatment, and heart failure. HFpEF, or heart failure with preserved ejection fraction, is heart failure is the leading cause of death of males in the Saudi Peninsula. And so we're very interested in dealing with heart failure with preserved ejection fraction, which is a fibrosis-related disease for which there's no good treatment. So this is one of the things we view as beginning in the Saudi Peninsula, is to try to look at this particular condition, which is a major killer here. Another major issue in Saudi and in the UAE is consanguinity. And this results in an accelerated aging-like state that, where we see a lot of residents of the Saudi Peninsula are exhibiting signs of early aging processes 10 years before they should. And this could be related to consanguinity. So these trials, some of the trials have been published, the early phase trials with arguably promising results, but this is only looking at target engagement, safety, and tolerability. The rest of the trials are double-blind and placebo-controlled and FDA regulated. Won't know the outcome of them for 2 to 5 years. As was mentioned earlier, things that sound too good to be true usually are. Clinical trials generally fail. A phase 2A trial has a 5% chance or so of working. And this is why we're trying to do multiple trials in parallel around the world, not just in the US. We've got partners in Asia too, especially in Singapore and Japan, to try to do these trials in parallel rather than in series so that we can test this very quickly. I'd be very cautious about using these agents outside the context of clinical trials. I lie awake every night. I hardly get any sleep because I'm worried about someone having a horrible side effect from one of these agents, because that happens. So far, we haven't had any serious adverse events that appear to be study drug related, but it doesn't mean it couldn't happen in the next few minutes. So we really need to do this in a careful way and carefully controlled clinical trials. This is going to take state actors to promote. This is beyond philanthropists. The individual trials are funded by various branches of government in the US, by the National Institutes of Health, by the military, as well as by foundations. There are going to be implications for agriculture. We see development, we've got early data indicating there could be increases in wool production, for example, in aged animals in quality, increased milk production, and increased egg production by older animals. Arguably, if these interventions work, they could affect developing countries to a far greater extent than developed countries, especially sub-Saharan Africa, where in 3 years, the number of elderly is going to exceed the number of children for the first time ever. So I think it's imperative that we move quickly, but cautiously, and chances are overwhelming that we'll fail in most of these trials. We're hoping that by doing multiple trials, we'll get the occasional win here and there. This is a tough process, as the other speakers have mentioned. Thanks.
Thank you so much. So as you can see, great progress is being made in increasing our health spans. But I now want to turn to Dr. Suwaidi to talk to us about what your interest is in the subject of longevity and what you are doing at the Dubai Academic Health Corporation.
So, thank you for this invite. We heard from the optimistic and the less optimistic, maybe the more pessimistic side, and I'm a realistic, an optimistic realist. I'm just going to share some of the background of my career and how this is related to the topic today. So I'm a family physician by training. Family physicians work with all age groups. We deal with individuals, families, from birth to death. We discuss challenges people face physically, mentally, socially. We're advocates to our community with policymakers, so we live with our community. And I had the privilege to serve the community of Dubai and move into other interesting areas where I was privileged to participate with the space mission, our first astronaut, Hazza al-Mansouri, following his health before, during, and after, and involved in many research with the space program. Longevity is a very, I mean, do you want to really live forever? It's a very interesting question. I think it's a choice. Mortality is important, I believe. It's a motivator for us to work, but again, it's a choice that individuals or society would make. For me, personally, it's very important not how long we live, but how we live. The quality of our days. This is, I see it every day in my work as a physician, and the opportunities that we are having with collaboration with other industry like space, for example, is also increasing our insight to support aging on Earth. I'm an assistant professor at Mohammed bin Rashid University of Medicine and Health Sciences, and we have a research group with the support of Mohammed bin Rashid Space Center to look at the bone health, the mobility of humans on Earth, through understanding the mobility within analog missions and also on the international space stations. And there's a lot of possibility of learnings that we can bring back and to support our community here on Earth. Really what my personal, I had a dream a few years back before the pandemic that people choose to live in the UAE because of its health system, and I think we are living this today. And my next dream is to have people live healthy and safely here in Dubai and in the UAE. And with all the interesting discussion we heard about the different applications of research and science, and we do have hope in bringing that knowledge into the care. We heard in the morning we want to move away from supporting the sick into preserving health for the community. And I'm also privileged with the team. A lot of my colleagues are here, and we challenge each other how we can improve the health system for the people of Dubai, not just for Dubai. Today, our vision is to advance health for humanity at the Dubai Academic Health Corporation, and opportunities to work and collaborate with different researchers, agencies, and challenging the status quo is actually what keeps us and motivates us to move forward. Thank you.
Thank you so much. Staying with you over there, I have a question around, I suppose the subtext here is that when you talk about immortality or the anti-aging, or it's really a question of access to healthcare, right? So a lot of this is both a personal choice as to what we as societies, as governments, allow people to do in terms of experiments, in terms of science and research, experimenting on their own bodies, even getting into the biohacking space. But on the other hand, you've also got questions around inequality of access to even basic healthcare. When we're talking about societies across the world where some people don't even have access to basic healthcare at all, and now we're talking about very advanced, very expensive technologies on the other end. In your perspective, is this pursuit of longevity something that should be directed by government policy, or is this something that should be left to individuals in the private sector, or perhaps the wealthy, to pursue and to continue on with?
Maybe I'm not the best person to answer this question, but I'm a strong believer in co-creation. We need to co-create policies that affect us as humans, and we do have in the UAE a very agile and responsive and proactive government that involves, and we heard Her Excellency speak about how we are rethinking and reimagining our legislative efforts in supporting these new technologies, and I think that is really for the community to decide going forward.
Thank you very much. We're running out of time now. I want to go back to Jose and going back to the more sort of far futures thing, because we do have a lot of futurists in the room here today. We've heard from the other doctors about how they are working on curing or at least preventing or slowing down various of the ailments that are reducing our quality of life or our health spans. But to put on our futurist hats and look a bit further ahead, let's go back to that question of longevity, escape, velocity, and what that really means, and if that is feasible or if that is something of a pipe dream. How much are you committed to those numbers that you put on the screen in terms of us actually being able to supposedly cure aging, as you speak of?
First of all, we heard yesterday Michio Kaku. Michio Kaku talks openly about immortality. I also believe this is possible, and I repeat, and you know, Alex, we are very good friends for a long time, but I am an engineer, working still as an engineer, and to me this is a technical problem. And the fact that I mentioned cancer discovered how to stop aging, and cancer didn't go to university like you or me. So if cancer discovered it, you are not going to discover it? I hope you are, because at least at MIT we will. And that is why I have these numbers, because Ray Kurzweil, who was my boss when I was at Singularity University, wrote this book that will come out next year, and he emphasizes those two dates, 2029 to 2030. And that will make us live long enough to live forever, but aging, because by 2030, those who make it by then, and I hope all of you will make it, we will gain an extra year per year we survive. I think these numbers are very realistic. Ray Kurzweil is 75, and he believes himself he will make it. I'm younger than him, therefore I'm even more optimistic that I will make it. He's director of engineering at Google, so I think he knows what he's talking about in certain areas. And yes, I believe in this, and I believe in 2045, if not before actually, we will have rejuvenation technologies, because we are very close, 5 to 10 years, to understand what cancer is doing. Now that we can sequence the genome, and I invite you all to sequence the genome here in Dubai with Dante Labs for a very cheap price, by the way. Now it's not $1 billion, it's just a couple of $100, and you can have it in a few days. So yes, this will happen. I'm totally convinced, and I want you to live long enough to live forever.
On that optimistic note, that's all we've got time for today, but can we just see with a raise of hands who actually would like to live forever if medical science gets us to the point where we can do that? That's quite a split result if you want to look around, but thank you very much.